Great. Hello and welcome everybody to this week's Intersystem Statistical and Random Geometry Colloquium. Today we're extremely glad to have Pierre-Francois from Imperial College London, who give us a talk on critical exponents for 3D percolation models with long-range dependence. Over to you, Pierre.
Okay, so thanks, Shubhajit. Thank you for the invitation. It's a great pleasure to speak in this capacity. Can you hear me all right, or is it okay?
Absolutely. Yeah, perfect.
Okay. So, okay, so I'm aware that people might have slightly different backgrounds. So I guess you know, if something is unclear, then by all means interrupt. I'm afraid I can't see the chat, but you know, maybe Shubhajit can help.
Yeah. Don't worry about that. Yeah, sure.
Okay, great. Let's see if this is working. Okay, so let me start off with some sort of classical things. So here is probably the simplest example of what you could call a second order phase transition. So this is called percolation. And it goes as follows. So you have a local density parameter, P, which is a number between 0 and 1. So this is a varying parameter. And then by some local rule, you decide to open either edges or vertices of some graph with probability P. So what you see in this picture here, and in both of these actually, is kind of the simplest local rule of all, which is basically just independently for every edge. So here it's the edges comprising the square lattice. You decide independently with probability P to retain the edge, and then you draw it black, and otherwise you just erase it. Okay, so if P is small, you know, most stuff gets erased. You get a picture as you see here on the left, and if P is rather close to 1, then you see this picture on the right. Okay, so it's immediately clear from the naked eye that these two pictures are somehow very different. Okay, so one way to see this is that if for instance, I send you to the back of the room, then the picture on the left will essentially look white, and the one on the right will essentially look like the full lattice. Okay, so now one way to measure this difference mathematically is by the introduction of what's called an order parameter, at least in physics. So here we're going to measure this difference by this function theta of P, which is the probability that any given point, say the origin in your lattice, is connected to the boundary of any box so of ever so large radius n. Okay, so here on the left, this probability is equal to 0, and here on the right, at least in this sample, it does indeed look like you are connected to the boundary of a box of arbitrarily large radius. Okay, and what do I mean by connected here? Well, you're only allowed to use edges which have been retained after this erasure. Okay, so you're only allowed to walk on edges which are open or black, if you prefer. Okay, so kind of in physics parlance, I guess, you know, you would call this a high temperature disordered phase where there isn't really any large scale structure, whereas over here there is, as measured by this function theta. Now I should say that you might not be familiar with percolation, and that's fine. So if you want something which maybe is more familiar to you, just remember that some of these percolation models, so for instance, if you think about Edwards-Sokal coupling, then you know, there's a certain percolation model where the probability to connect 2 points x and y corresponds exactly to a spin-spin correlation function, so to a 2-point function in some spin model. So you can really, think of these as the same kinds of phase transitions that you see, for instance, at least qualitatively, as you see, for instance, in Ising models or other models exhibiting a second order phase transition. Okay, all right. But this talk will be about percolation, so we'll stick to this. And so here, there is an obvious way in which if you increase p, then this function theta increases, and so you can define a critical parameter to be the supremum over all p, such that theta of p is equal to 0. So on the left, you see that clearly 0.2 is less than PC, and 0.8 seems to be greater than PC. Okay. So what I want to do in the next 10 or 15 minutes or so is I want to try to advocate and recall, I mean, it's well known, a slightly different way of thinking about the phase transition, which in a sense is less singular. And basically, PC is a nice, well-defined mathematical quantity, but for instance, in practice, you only ever have access to a big finite chunk of the lattice. So you can't really define this observable, which is kind of in the infinite volume limit, and so it's better to think in terms of sort of a zone or region of P's where the picture looks critical, and this brings about this idea of correlation lengths that diverges at the critical point, which I want to review next. Okay, so to see that, consider a picture which, so here this is a sample around PC, and if you look at this picture and I pick a point somewhere in the middle, then you're going to have to spend a minute or two to see whether this point is actually connected to the boundary or not. And I think this particular one isn't, if I'm not mistaken. So here is a little help. So here I drew some clusters. So you see that near the critical point, you see these sorts of mesoscopic clusters which look fractal. So that's the picture that you see. And one thing, of course, which you learn by doing these simulations is that this function theta of p appears to change continuously across PC, right? It's not like one moment there is no infinite cluster and the next it's there. It sort of grows organically in a sense, and this is the archetype of what people call a second order phase transition. Okay. So now, of course, when you simulate this on a computer, you're interested in sort of seeing the critical phase, which is the most interesting bit about the phase transition. And so there is a very practical question, which is that if you're close enough to PC, I mean, how big should your window be in order to see a critical picture? And you see here, for instance, if you draw this blue box, which is commensurate with the big one, I mean, it's only 2 or 3 times smaller, then, if you forget everything that happens outside of the blue box, then in fact, this point still looks somewhat well connected to the boundary. So you may, erroneously conclude by just looking at this that this is in fact supercritical, when in reality it isn't. Okay, so now what's the good way to think about this near critical regime? So here is how physicists like to think of it, at least intuitively. And so this goes under the name of scaling theory. Okay, so let me focus on just one observable for the purpose of this talk. And I'm just going to take the simplest of all, which is just the probability that 2 points, 0 and x, are connected. Okay, so here is 0, and you think of x as a faraway point, and you're especially interested in this when x sort of recedes to infinity. Okay, so the intuitive picture that you get from the pictures I just showed you is that in fact, at all, including the critical point, this 2-point function should go to 0 as x goes to infinity. And what what physicists expect is that, in fact, at the critical point, this function has polynomial tails. So this, this is kind of relates to this idea that at the critical point you see these mesoscopic clusters which are kind of fractal and have sort of polynomial tails. And so this is putatively governed by a polynomial decay with an exponent which is commonly called eta. Okay, this is a conjecture. I mean, it's of course corroborated by numerical experiments. And then, okay, so this is at the critical point, and if you say you go down from the critical point, then you expect that this function behaves in the following way. So if you vary p, then for a while it's just going to look like the critical 2-point function, and then you're going to start to witness the subcritical phase, so the phase below pc, by means of this function f, which is a rapidly decaying function, and you're going to witness this decay in units of a length scale psi, which is called the correlation length. Okay, so think of this function as being sort of an exponentially decaying function, and the argument is this ratio. So this decay starts to kick in as x starts to grow in multiple of this length scale psi of p, which is the correlation length. And the expected behavior of this correlation length is that as you approach pc, this length scale diverges, and it diverges again polynomially in the distance to pc with another exponent, which is usually called nu. Okay, so that means that over here on the left, the answer to the question, okay, if you want a good resolution of a critical a picture at a value of p which is close to pc, then the size of the box should be roughly psi of p. This is the scale until which you will see a critical picture. Okay, so now let me just do a little something, because here we've only been talking about p less than or equal to pc, and I want to talk about all p's at once. So of course, if I start to go above pc, then this 2-point function tau p does not decay at all. In fact, by something which is called the FKG inequality, you can easily see that it's bounded away from 0. So the way to fix this and sort of treat both regimes less than PC and bigger than PC simultaneously and symmetrically, you introduce a truncation. So you look at the probability that 0 is connected to x, but not to infinity. So of course, when you're below PC, this has no effect, and this is just equal to the function I defined up there. And above PC, it removes this issue. And then the expected scaling of this function for any value of p now is exactly the one that I wrote here. And I should say, okay, what do I mean by these wiggly lines here? So I mean that the left-hand side and the right-hand side are, comparable. So it's greater or equal or less than or equal up to numerical constants, which depend only on the dimension of the lattice, so on geometric properties, and this comparison should ideally be valid for all values of x and p. Okay. All right. So so these two exponents governing the correlation lengths and the scaling behavior of this 2-point function at criticality, these are just two among a series of 8 or more, depending how you count, so-called critical exponents. And well, they're in fact not all independent. So if you stick to these 8 that I have in mind, I won't define them all for you here, but sort of the scaling theory will tell you that there are 6 conjectured so-called scaling relations between them, which are just linear equations relating these exponents. So basically, if you know 2 and you believe in these equations, then you know all of them. And what's important is that these exponents are objects which physicists crave because they're expectedly universal. So what this means is that the local rule by which you define your percolation model, by which you declare how to open or close edges, should not influence the value of these exponents, as long as you, do not change the local rules too much. So this defines what people like to call universality classes. Okay, so for percolation, here are some known results. So this is really about independent percolation on ZD, where you declare independently at every vertex or bond to be open or not. So in 2 dimension, there is, of course, been great progress, and we know, for instance, the value of these 2 exponents. So we can prove that they exist and determine their value. So I should say we can do this specifically for side percolation on the triangular lattice, but still, I mean, there is a model where we can actually determine these rigorously. So this is, of course, a celebrated work. And then when D is high enough, so I never quite know for sure where we stand, might be that this 11 can be 10. But basically, when the dimension is large enough, you enter what's called mean field regime, and then somehow these exponents, I mean, the behavior of the system is not really influenced by the underlying lattice anymore. So this has to do with the fact that, for instance, if you're on a high dimensional Euclidean lattice, then locally things look like on a tree, and it becomes very hard to close loops. So it looks like a percolation in the mean field regime. And then this is exactly what happens. Okay, and conjecturally, this is, at least for percolation, this is supposed to be true starting at what you would call an upper critical dimension, which is expectedly equal to 6. But we're not quite there yet. Okay, so this is sort of what's known in the world of Bernoulli. And so a lot of my research goes into trying to understand some percolation model in sort of the intermediate regime, so between 2 and the upper critical dimension. And so that's going to be the goal of this talk. So it will be to study some percolation model in these difficult intermediate dimensions. Okay. And maybe one takeaway of the talk is of course, there has been already, this question has been investigated for the IID percolation model, which, is the simplest one to define. But it turns out that in intermediate dimensions, it turns out that, the simplest model to define is not necessarily the simplest one to study. Okay, so the percolation model that I'm alluding to here is not going to be Bernoulli percolation. It's going to be another model, which I will introduce now. Okay, so here it goes. So let's take Z3, the 3-dimensional cubic lattice for now. And so these models that I'm going to define, they were introduced originally, I mean, this one specifically by Leibowitz and Saller in a paper of 86, and there are other references which introduce similar models. This one was the first one to study it actually rigorously. Okay, so the model is the following. So imagine that you have a random field indexed by the vertices of your graph. Okay, so you have your graph, and at every vertex you have a random variable sitting. So you have this kind of landscape. And I'm going to assume that phi is a centered Gaussian process, so it has mean 0, and it's stationary. And I'm going to denote its law by this double bar P. Okay, so you can immediately build a nice percolation model out of this simply by looking at the excursion sets. Okay, so you fix a height parameter h, which can vary. And then you sort of chop off at h, and you look at the vertices where the landscape exceeded this value of h. So you look at kind of the tips of the mountain. Okay, and now you vary h over the reals. So I'm slowly going to change from parameterizing by p, which is a density parameter, and I'm going to replace it with h, but it's just a different way of parameterizing things. Okay, and of course here, I mean, the simplest model is if you take uncorrelated Gaussian sitting at every vertex, and then you just have the usual Bernoulli side percolation model. But here we want to do something sort of rather different, and what I'm going to look at is a different landscape, which is called the Gaussian free field. Okay, and this is characterized by saying that correlations are given by the Green's function of the simple random walk on the graph. So since you're in 3 dimensions, the walk is transient, this is finite, and it in fact decays like distance to some small power a, where a is d minus 2, which is equal to 1 in dimension 3. Okay, so this, this is sort of puts you in a different universality class, presumably, because these, this decay of correlations is so strong that you do not expect, for instance, this model and this model to have the same critical exponents. Okay. All right. So this is the field, and now the model comes in sort of 2 versions. The first one is the one I already defined. You just look at the excursion sets of this Gaussian free field, and the second model is a sort of refined version which has greater integrability properties, but is presumably, I mean, it's not clear yet, in the same universality class. And it goes as follows. So there is a slight twist. So first you sample this Gaussian free field phi, and then on top of this, there is sort of a disorder on the bonds. And after you sample phi, you keep any edge independently with a probability that I wrote down here. So to keep the edge, of course, you need phi at both endpoints to be bigger than h. Otherwise, the probability is 0. But you need more than that, okay? So you need the endpoints to have value bigger than h, and then you need this extra bond disorder to actually retain the edge. So it's harder to percolate in model 2. Okay, so here's a slight illustration. Okay, now these open paths that I'm talking about in the landscape. In the first model, you can walk along any edge where the 2 endpoints have a value which is greater or equal to h, and in model 2 you have this constraint plus the extra constraint that the bond variable is open. All right. I'm not going to go into details as to why this particular bond disorder is interesting, but well, if you ask me, I can explain that at the end of the talk, for instance. All right. So now I just want to rephrase the questions I was asking for these 2 percolation models. So here it goes. Okay, so now you have for each model I equals 1 and 2, you have the open edges or vertices of your graph of the 3-dimensional lattice in model I. And there is a corresponding critical parameter, h star, which corresponds to PC, which is just the smallest h, such that the probability to connect to far away is equal to 0. Okay, so here, when you raise h, you see less stuff because the tips of the mountains get sparser and sparser. So here, the picture is the other way around, right? So the disordered face sits on top of the order. Okay, and as I was trying to allude to, and this is in fact a theorem, it's a combination of several works. The 2 critical parameters for the models are not the same. It's really harder to percolate in the second model. This additional bond disorder makes a difference. But that's okay. I mean, the value of the critical point PC is not a universal quantity. It's supposed to change. I mean, these exponents are only phrased in terms of things that happen at the critical point or are measured in terms of the distance to it, but not in terms of the actual value itself. Okay, and so the big question is whether these models 1 or 2 are part of some universality class, which is whose critical exponents can be somehow captured. Okay, so it's the usual question, and if you sort of read what physicists have to say about it, then what they tend to say, which I think is a bit too well, it's certainly not true in this way, but somehow to a large extent this universality class should be determined by how quickly the correlations between 2 points in the model decay. Okay, so and here we're in a class where basically the decay is some sort of small polynomial, and somehow this exponent a should dictate these exponents. Okay, so I'm just going to ask exactly the same question that I mentioned before. I'm just going to look at this truncated 2-point observables in each one of the models, and the scaling conjecture, which one would hope to turn into a theorem, is can one prove that the truncated 2-point function has the scaling? So here there is an h star missing. I'm sorry about that. And of course, to write this, I mean, you need to understand what this correlation length psi is, how it scales, what is the exponent nu that comes with it, etc. Okay, so now I'm going to give you some results. So first for model 1 and then for model 2. So here is a result about model 1. This is joint work with Shubhajit and also Franco Severo. So the result is the following. If you look at this truncated 2-point observable in model 1, so these were just the excursion sets of the discrete free field, then as x recedes to infinity, we can determine very precisely the leading asymptotics. And it turns out that this function decays exponentially like x over log x, and the dependence on h minus h star is explicit. Okay, and in dimension 4, we can show that this decay is exponential. All right, so let me make some remarks about this. So first of all, this fits within sort of long body of work on large deviation type results for the GFF, and I mentioned some of the relevant contributors here. So the more recent works have to do with observables related to this percolation phase transition, and in the earliest works, so this particular one, which maybe arguably initiated the story for the free field, looked at something much more basic but already quite interesting, which is just how does the probability behave if you force, for instance, everything inside of a box to be bigger than 0? So this is this hard wall condition, and because of these strong correlations, there are already interesting phenomena that appear. So this is completely different than what would happen if the random variables were completely independent. Okay, so now returning to our theorem, so there is. Let me focus on d equals 3 because that's that's the setup I chose. So the first thing we learned is that the decay is actually not exponential but sub-exponential, and so I'm not going to go into the details of why this is, but this has to do with the fact that the cost of creating a long path of length x turns out not to be measured so much by the diameter of the path, but rather by its capacity in the context of the free field, and this is where this factor appears. And in fact, there was a long discussion about how this function should really behave, and people didn't necessarily agree. So we settled this question. And but the perhaps even more important thing is, so even though this does not quite show the scaling hypothesis that I flashed earlier, because this is only in some sense an asymptotic result when x becomes large, it teaches you one thing. It teaches you that if this scaling hypothesis holds, then you can in fact identify well, the leading exponential decay. So it's what I said, it's this exponential in x over log x function. And more importantly, it also identifies what psi has to be, because we have this explicit dependence on h over here. And and this shows you that, well, if you have the scaling here, so let me show it to you again, right? Then this function psi has to be h minus h star to the minus nu, with a value of nu which is equal to 2. And this, in fact, confirms a conjecture of physicists, namely Weinrieb and Halperin, which is that, loosely speaking, if you're in a long-range class with exponent a, so remember a was the exponent governing the decay of local correlation. So here it's d minus 2, which is 1 in dimension 3. Then you expect, so if this exponent a is small enough, and if this order is relevant, as physicists would say, you would expect the correlation length exponent to be 2 over a, which, well, you know, if a is 1, u is 2. So this is exactly what we get here. Okay, good. So this is about model 1. So now I'm going to talk about model 2, where we can go sort of one step further. Okay, maybe before I do that, let me, this is maybe important. So, you know, I told you, I mean, it's in dimension 3, for instance, studying Bernoulli percolation is a hard problem, and progress is slow. And so, you know, when you see a theorem like this, I mean, this is very good news, because this already goes way beyond what we can do for Bernoulli. So, you know, just for you to witness this. So first of all, in Bernoulli percolation, there is no reason to expect in dimension 3 that this value of nu is nice. So, you know, here it's a rational number, but for Bernoulli, presumably won't be. It has no reason to be. And the best rigorous results we have do not even witness sort of a polynomial dependence on h for the correlation lengths. And of course, this is related to the problem of showing that the phase transition is continuous. Okay, so here is now a model 2 where we can sort of improve on these results even further. So this is joint work with Alex Dritz and Alexis Prévost from last year. So I'm still in dimension 3, and what we can say is that for model 2, actually the scaling hypothesis almost hold. So what this means is that with the same correlation length, so it's still h minus h star to the minus 2 as we figured out in model 1, you can prove the following upper and lower bounds. So you see now really that, so there is a critical 2-point function, and then a decay, which is this function x of x over log x, and it's, okay, there is it's not exactly a function of x over psi. Maybe we can actually improve on this now, but almost. And the lower bound is actually a function of x over psi. And so what's important, of course, in all these estimates is that they be true ideally for all x and h. So the upper bound is, and the lower bound isn't quite, but it's in fact good enough for many practical purposes. So okay, the first condition here is not important. This is not, I mean, anyways, we want h to be close to h star. Here there is a small condition on x being large enough, but in fact not too large, and I'll get back to this condition in a minute. Okay, so here are some remarks about this. So it turns out that the critical 2-point function can
Sorry,
be...
Pierre.
Yes.
Sorry. So just so the lower bound is essentially like what you would, what the scaling hypothesis say, right? In the upper bound, actually, you're just.
Except for this condition here.
Okay, I see.
Which is not a, okay, so I can say it now. So it looks fairly innocent, but you see, I'm about to tell you that from these two things, you can deduce, for instance, a scaling relation, which is Fisher's scaling law. And just for you to appreciate how good your estimate needs to be. So for instance, if we had this lower bound here with an exponent delta, which was not between 0 and 1, but say 1 or something bigger than 1, then already I couldn't infer the scaling relation. So you really have to make sure that you don't need to take too large an x, depending on psi. Ideally, in fact, it should be valid for all x with no constraint. Yeah, so this is the small defect here, and the defect in the upper bound is that this log is not measured in units of psi. So the two have small defects in some sense. Okay, so all right, so the critical two-point function, in fact, so this is one instance of the integrability of this model can in fact be computed fairly easily, and that this was observed by Titus Lupu, and it turns out that that eta is equal to t minus 2. Okay, I'm not going to enter into explaining this picture, so just forget about it. Maybe one thing I'd like to mention is exactly this. So if you look, for instance, at the mean cluster size, so this function chi of h, which is just the sum over this truncated two-point function over x, then these two bounds are good enough to show that if you look at the log of this function chi divided by minus log of absolute value of h, then as h tends to h star, this limit exists. So these small deficiencies that I mentioned will not spoil the existence of this limit. And
so here you're using this a star equals to 0, right? So that's there. When you, usually
you don't need to know that.
So then actually in the definition of gamma, you should divide by log of the distance from the critical value.
Yeah. This is, yeah. But if I write h minus h star here, then h star 2, then yeah. You don't need this information to do this calculation. Indeed. Yeah, so I should, if I write this, I should write minus h star here. You're completely right. Okay, so this exists and is equal to the value which is predicted, and this is one instance of a so-called scaling relation. Okay, so this follows, but in fact these bounds are stronger than these scaling relations. So I should mention, so there has been some work on this model too by various people. So first there was a paper by by Titus that I already mentioned. And also Snitman. Then there was a paper by Dingwild where they proved an upper bound like this for the one-arm probability, but in fact it's weaker because there isn't the right prefactor. Then in earlier work we also looked at this problem and trying to understand where the integrability really came from. So in earlier work, we showed that, in fact, at the critical point, which Shubhajit already pointed to, is equal to 0, the capacity of the cluster of the origin is, in fact, always finite, so on any transient weighted graph. And in most cases, the capacity being finite implies that the set is finite. And this is why you can prove in most cases that the phase transition is continuous. So it's due to this quantity here. The cluster capacity is an integrable quantity for the model. And then there's been also work by Wendelin on this model and above the upper critical dimension, so in dimensions d bigger than 6. The nice thing here is that you can really see, go down to to 6 in these considerations. Okay, so let's see. So yeah, in the time that remains, I want to at least explain where this correlation length comes from and how you should think of the model as implementing this connection between 0 and x. Okay, so here is sort of an attempt at relating this to you. So one important tool that you use in dimension 2 is often what's called a duality symmetry. And I'm just telling you this for a sort of analogy purposes. So often you know that if you have a duality, then the probability. I mean, you have this topological effect which you can harness, which is that either you have a open path going from left to right, so this is now really two-dimensional, and if not, you must have a dual path going from top to bottom, and if you're at the self-dual point, then both events have the same probability, so the probability to cross from left to right is actually equal to 1/2 on a square. And if you know this, I mean, then you already know that at this value of H star, I mean, at this self-dual point, you must be critical, because this is telling you that you have a sort of, I mean, forget that it goes from left to right, but that you have a macroscopic quantity with probability bounded away from 0 and 1, and so this is exactly a characteristic of the critical regime. Okay, so this is sort of an existence result. It tells you that you have big clusters with good probability. And then there is a sort of uniqueness tool, which is called the Rousseau-Seymour-Welch estimate, which tells you that, okay, so in fact, not only do you see crossing of a square with a sizable probability, but you can also cross a rectangle of any aspect ratio. And okay, so this gives you the existence of big things, and this is a sort of uniqueness statement, if you like, because once you can cross a rectangle, then you can start building with good probability the sorts of pictures that I drew down here, and this is effectively how you will start building longer and longer paths. Okay, so now when you want to go to dimension 3, you immediately have a problem, which is that this sort of topological duality that you used, you cannot, I mean, you don't have this anymore, right? If you have an object which has a dimension which can be as small as 1, then the codimension is 2, so this vertical thing is not at all necessarily a path. So how to go about this? Well, so the solution comes from thinking naively. Well, so for instance, let's say if this thing had dimension 2 and you are now in 3 dimension, then the codimension would be 1, and so you can't fit two-dimensional objects inside of a 3-dimensional box, which will not touch. And this is exactly the thing that we somehow use here. And so now there is a sort of a relatively involved a story which goes under the name of isomorphism theory, by which basically you can, so this is not really true, but it's good enough for the purposes of this talk. So what I want you to think of is I want you to think of open paths as being random walk trajectories, which then really become two-dimensional objects. And then this sort of intuition would be true. And so it turns out that for the specific model 2 that I introduced, there is such a way to use this as a sort of dictionary and use this kind of random walk representation for your model. And so the theorem that we prove, which is relevant for these lower bounds, is the following. So if you imagine that you are in the supercritical regime and you're at a distance epsilon from the critical point, then in fact, what happens is that the probability to connect two boxes of commensurate size by an open path is, so h is really at distance epsilon from the critical point now, behaves like 1 minus e to the minus epsilon squared times the capacity of the box. And moreover, so this would be sort of an existence result, if you like, not quite at the critical point, but with at the distance epsilon away, but with probabilities which are sort of quantitative. And then
so here you don't have any restrictions on L or anything.
No. This is exactly
okay.
This
yeah.
is true.
Yeah. Mm.
And importantly, there is a corresponding uniqueness result, which is also quantitative, which tells you that you can connect two crossing objects with the same probability inside of that box. Okay, and well, these two things put together will allow you to start chaining things and build longer and longer things, a bit like the picture I was doing up here. And what's important is that, well, you can do this when this probability is sizable. And when is this probability sizable? When, well, exactly when this is of order 1. So the capacity scales like L to the d minus 2. And that tells you exactly how this, this characteristic length scale psi should be for this to work. So in a sense, the way that the connection is happening here is that somehow at the critical point, you create a blob which, at the critical scale makes itself, grows to have the right capacity so that it's actually visible by one of these random walk trajectories. So this is this critical cost here. This is creating something which large enough capacity. And then these random walks that I was drawing, they start to implement the correlation, the connection to further and further points x, and this happens by means of this tool here.
So what you just said here, so this fact is not three-dimensional, right? It's just this particular thing that you said.
Right. So what is 3 or let's say less than 4-dimensional is that when you want to start, I mean, the whole issue is exactly this. I can show it here. So here, I mean, if these two red things are, say, for instance, random walk trajectories, to make it simple, then this is only true in dimension less than 4, right? Because well, the two walks will intersect in many places, but when you go beyond dimension 4, then and the connection mechanism is more complicated. So this picture starts to break.
It's about this intersection property of random.
In some sense, yes, indeed, absolutely. Okay, so this was for the 3-dimensional lattice, but so now you can go back and look at what we did and see what really we have been using, which underlying properties of the graph we need, and it turns out that our results are relatively robust. So imagine that you have the following conditions. So now G is not necessarily the 3-dimensional lattice; it's any graph. And it has certain properties characterized by 2 parameters D and A. So first of all, I want there to be a volume growth of balls of the order R to the D. So in some sense, D is a dimension for the graph. And these balls, they are measured, for instance, in the graph distance, but not necessarily. But they have to be measured in a distance for which you can say that the Green's function decays like that distance to the power minus a. So this is this other exponent a. And in fact, I mean, there are cases, interesting cases, for instance, when you take products of graphs where, if you diffuse in one coordinate faster than in the other, then the graph distance is not necessarily the canonical choice over here. But of course, these two I mean, for instance, the planar lattice is not in this category because this implies in particular that the Green's function is finite, so you're in a transient setup. Okay, and so our theorem, you can rephrase it as, so if you have these two conditions, so this is a geometric condition on the graph, and this is an analytic one, if you like, and if A is less than or equal to 1, then these bounds that I showed you hold true. Okay, so this is you know, some level of universality, and it means, for instance, that our theorems apply. So there is a nice example that I like to give because this is interesting for a related problem, which is the disconnection problem. So if you take a cylinder which is Z cross this kind of graphical Sierpinski gasket, then this is actually a graph whose dimension you can think of as being between 2 and 3, and the walk on this thing is actually subdiffusive because these traps in the carpet, in the fractal, they kind of slow you down at every scale. So this also very much applies in cases where the walk is not diffusive at all, but rather subdiffusive. And these things, you know, have been, of course, studied by various people, some of which I mentioned over here. Okay, I should also say that these two conditions, I mean, they don't fall out of the sky. They're in fact extremely natural. And for instance, if they're true with respect to the graph distance, then it's a well-known theorem by Grigorian and Telks that these two things are equivalent to a two-sided heat kernel estimates for the walk. So in some sense, you know, if you look at what people did in the realm of studying just the diffusion of on these graphs, then these conditions naturally appear. So in some sense, it's not that surprising that it is what it's important for us as well. Okay, and so now you can sort of at least play a little game, right? So we determine two exponents, eta and nu, and I told you there are 8 in total. So here is all 8 of them. So I'm not going to define them all for you because it doesn't really help the discussion at this point. And so the expected behavior is that you have these 6 linear relations, which should all hold in intermediate dimensions. So here there's only 5 equal signs, but there is one which we actually just proved. And so now you can take, you know, eta and nu, plug into these equations and see what you get. And what you get is the value of the exponents that I wrote down here. So it turns out that I focused on nu and eta over here, but we can say quite a bit more rigorously. So the red stuff is everything we can make rigorous statements about. So in fact, you know, by our findings, this table is heavily overdetermined in a sense. But yeah, so I'm happy to report that the physicists were right, as they often are. So there is a unique set of exponents which are thereby determined, which are the ones that I wrote down here. And all of these exponents have rational values, which are functions of the underlying dimension and the decay exponent A. So these are these 2 parameters which came with the graph. Okay, so in fact we're you know, hopeful that we can push this to A equals 2, but then you know, the story will become more complicated as Shubhajit was already alluding to. And you know, but you can be even bolder and you know, pretend that maybe this is actually always what you should get. I don't know, and beyond A equals 2, I don't have particularly a strong reason to believe that, but curiosity that is at least noteworthy is that so if you push A to 4 and D to 6 in this table, so this corresponds to reaching this presumable upper critical dimension 6, then the value of these exponents actually reach the mean field values. So, okay, so
just to put it in perspective, so like even though the critical exponent themselves may vary, right? The relations are supposed to be universal in a sense. Is that correct?
Yeah. I mean, the hyperscaling will break down beyond the upper critical dimension.
Right.
Then things will not depend on D anymore. But you can, So, in intermediate dimensions, all of these should be true. And of course, this. So it's good that we can actually see these exponents, and now these models that I introduced relate to many other models. I mentioned a few: loops, vacant sets of random walks, etc. And so you wonder whether or not these exponents describe those models as well. Another class of models, which is of course related, is that of long-range Bernoulli percolation. So where you add long-range bonds between vertices, so it turns out that some of these exponents seem to coincide, but the relation between the two, I mean, whether or not this defines the same universality class is not at all clear at the moment. And of course, for these long-range models where you have long-range bonds, they're in some sense less amenable, because these kind of theorems, like these estimates here, I mean, it's going to be hard to define a correlation length for these models, and in fact, physicists usually avoid this because away from criticality, you always have polynomial lower bounds to connect things. So somehow, if you naively define the 2-point function in the same way, just connecting 0 to x, then it's going to be one polynomial versus another polynomial. So this is kind of hard to detect. So somehow, you would have to define something which is connecting 0 and x using edges which are not too long, but how long should they be? I mean, this becomes more intricate, and here it's completely clean, and the observable is just the one you should naively write down. Okay, so on these words, I will thank you for your attention.
Thanks, Pierre, for the wonderful talk. Let's all thank Pierre for being today here. And are there any questions for Pierre? Take that. So for the transitive graph generic the setting that you mentioned, so you get essentially the full strength of the result. Is that correct? Or
yes.
With this assumption.
So there is a technical condition here which I didn't mention, but with a little epsilon. So if d is the graph distance, then this is enough.
Mm-hmm.
If it's not, you need to make sure that you can do. I mean, you need some sort of isoperimetry to be able to connect paths and do things. But say on graphs where this holds for the graph distance, then this is all you need.
Yeah. Okay.
Which is reasonable. I mean, at least when you come from a random walk background like me, then these are the natural conditions you want to put on your graph, because they kind of determine the behavior of the walk, and very precisely. So you do expect that if there isn't anything else, then that's relevant for the problem, then that should be it. So it's in some sense not surprising that these turn out to be good conditions in this percolation context as well.
Great. Okay. So if there are no further questions for Pierre, let's thank Pierre again. And so okay, see you all next week. Thanks, Pierre, again. Bye.
Yeah, thank you all for coming.